We're going to investigate combining electric and magnetic fields and going to look for motion. We're going to use this apparatus here, a DC current supply. Number one, the vertical wire. We're going to look for motion. And number two there, a horseshoe C-core magnet. And be very careful because we're going to use 8 amps and you're not going to turn on the circuit until you're demonstrating the experiment. And here's some more safety precautions and pause to reread. Because of the high amps, you want to be nowhere near it when it is turned on. It is a teacher demonstration only. No direct student involvement, and students should be at least 10 feet, 3 meters away. And make sure the current and the voltage are turned off after a short usage because you'll melt the wires. The procedure here, the setup as shown, only turn on for a small amount of time, get hands well away from it, and after 3 seconds you're going to turn it off. Here's a close-up of the equipment, a DC power supply, horseshoe magnet, some flat copper tape, the vertical wire where you're going to look for motion, and your multimeter, ammeter for measuring and controlling the current. And the fingers here are a long way away from the wire, and the current is not turned on at this time. In the diagram on the left, you haven't got the horseshoe magnet in place. This is the actual circuit of the wires. Conventional current is with the arrows going down at number one. And you're looking at the field lines around the vertical wire with the circular electric field lines around it, which we could plot with a magnet. We can also look at the right-hand rule where the hand, and again no current here, is going behind and around the wire, and the direction of the curvature of the fingers is showing the direction of the field lines. A circuit diagram from the diagram of the actual circuit. We're looking at the magnetic field produced by the horseshoe magnet, and the blue pole is your south pole. And here are the field lines from the horseshoe magnet going from north to south across the center of the magnet. Again, don't turn on the power until the circuit is complete. The magnet is in place, and yours, and indeed everyone else's fingers, are a long way from any of the wires. So we're going to investigate combining the electric field from the vertical wire here, all the circuit, but we're going to look at it, the vertical part of it, and the magnetic field from between the poles of the horseshoe magnet. And here we've got the current, number one, direction of current, number two, the field lines, magnetic field lines shown, and a close-up view of the circuit. And again, reminder, please don't touch. The magnet itself is made of metal, and if it touches the circuit, again, it's not what you want to be seeing happening. And here we've got a diagram of the motion, just still photographs of the motion. And we're looking again at the white dotted magnetic field lines between the north and the south pole of the magnet, the direction of current at the top of the diagram pointing downwards, and then you've got the motion of the wire which is moving outwards. and yet only leave it on for 3 seconds. And obviously when you cut off the power supply, the motion will stop. And here we've got left-hand rule. The thumb is not going to be dislocated to point quite out at M, but that's where it's going. The second finger pointing downwards, the direction of the electric field, and F, first finger here, the field of the magnetic field is shown. And here's the left-hand rule in the directions as experienced in this lab. And we're just going to look at a video of the lab.
Fantastic. Could we have it's not a spiral, because that's not going to work. That's a sort of helter-skelter shape, isn't it? What would be the geometry of the magnetic field around this? Give a better answer.
A 2?
A 2?
Yeah, cylinder.
Cylindrical. Brilliant. All good. That's the concept. Let's see if we can prove it. So we'll put this onto, I promise not to melt mode.
No.
Try again.
Yes.
Yeah, it's actually quite a lot. It's significant in terms of current. It's a bit morbid, but if you want to electrocute someone, you need to pass towards half an amp to an amp through their body. If you can get it to do that, you disrupt their entire system. But most of the time, the current flows over the surface of your skin. But an amp is a lot. So, is that a lot?
Yes.
Yeah, 8 amps. It's good. But you need that. And that's why we're not using regular wires, because the wires here, even at short burst, get a bit hot. So we'll have to look and be careful we don't melt anything, because these are the good wires, right? Now you know how the other ones got to be from this to how they are. Because some fool's been passing 10 amps through them on a regular basis, doing stuff like this, and eventually it just destroys them. All right, you know what this is. We'll take you out of the way. And at the moment, where's it pointing? It's pointing towards you. Are you magnetic?
Yes.
Cool. Where's it pointing?
To north, more like...
Geographic or magnetic?
Geographic.
Geographic, which means, what is the red?
The south.
No. We keep doing this, don't we?
North? Magnetic north.
Magnetic north, therefore it's pointing towards a...
Geographic.
No,
north.
magnetic
south.
south,
Magnetic south, geographic
which is
north.
the same place as where what well-known creatures live?
Polar bears.
Polar bears. Nice job. Why is it pointing down like that and not like that?
Because of the magnet is at the core of the Earth. Something like that.
Yeah, the magnetism could be represented by a large bar magnet buried near the centre of the Earth, and so the field that you're very familiar with penetrates the Earth's crust at a big angle. But the component points, the horizontal component points that way. Mm-hmm. All right, let's turn this on and see if we can get it to behave. Oh yeah, look at that. Before everything melts. You okay with that being circles?
Yeah.
Concentric circles? That's kind of cool, isn't it? Let's quickly turn them off before some. Probably it might be uniform in here, and it might curve a bit around the outside, but where that is, probably that way. Fair enough? Okay. We're going to pass a current, another 8 amps through it, and we'll see what happens. So at the moment we've got a wire carrying 8 amps in a minute, in a second or two, in a magnetic field. From your reading, what do you think might happen? I've got a magnetic field. Is there a magnetic field associated with this?
Oh.
When I passed a current through this, did we have a magnetic field around it? This is not tricky. Yeah. And this is a magnetic field. So when you put 2 magnetic fields together, what happens? Attraction or repulsion, right? It's much like 10th grade. Oh, I can say that, right? So that's mainly repulsion. And so you're going to get attraction or repulsion, but it's not easy. And let's just put this in, so you watch carefully. Oh yeah. And if you're clever, this is called resonance, by the way. Okay. So are you okay with the fact it repelled, or it went that way? Okay. Do you remember there was a rule associated with one of my hands? Right?
Left hand rule?
Fleming's left-hand rule. And we have to learn this. And if some of you are genetically challenged and you do outdo that, this is not going to work for you. You have to make 3 right angles here.
Yeah.
Fleming's left-hand rule. Okay, it looks a little like a gang symbol, but trust me, no one's going to arrest you for this.
Does it not work with the right hand?
It does, but that's for another day.
Oh.
This is the induction rule.
I can just do.
Now, let me say this
But it's
once.
the same thing.
This is to do with motion, forces on a wire. It's to do with forces. This is the very basis of a very important discovery from around, or an invention from around 1832. If you can make a wire with magnetism and currents move, what does that lead to? We have motion here, caused by currents and magnetism. Moving. We're moving things.
Oh,
A car?
like those trains
Yeah.
that have, like magnetic.
Right, good. A
Okay.
Tesla.
Okay.
At the heart of a Tesla is an electric motor with apparently some very clever things in it. This leads to an electric motor, 1832. It was invented in Britain. And it's an amazing thing to create an electric motor. And it's essentially from this. Hence, this could be called the motor rule, right? Because it leads to, it's the force on a wire, the motor rule. And therefore, how do you remember it's your left hand is the motor rule? It's easy. What side of the road do we drive on in England?
The left.
The left. How can you now forget that? It's the left-hand rule is the motor rule, and it predicts the direction of the force on a wire. And this is how it's going to go, unless you've got arthritis. Ready? Now, here's the current leaving here. The current is down. This is the current. Down. Now leave it down. This is the field. And my thumb is pointing towards me, which is the direction the force was in. Easy. Easy peasy, lemon squeezy. Love
Okay,
to.
current.
Second finger is the current. The first finger is the field, and the thumb is the force or the motion resulting from the first two. So what's really going on here? Well, what do you think is actually experiencing the force?
The electrons.
The charge
Nice
particle.
job, the electrons. Which way are the electrons going?
That one.
What way?
Down.
Well, hang on. If
Oh,
conventional current
down.
is
Yeah, down.
which way are the electrons moving?
Down. Out.
Up.
Out.
And who do we blame for this annoying mistake?
Edison.
An American, right. We blame Benjamin Franklin, who was way too gifted in too many things. He did not realise, and no one did at the time, that what was actually moving inside here were the electrons, not a positive charge. So he named current flow, conventional current flow, after a flow of positive charge, which in solids doesn't exist. It works perfectly well in liquids and gases, plasmas, but it doesn't work in solids. Let's go and look at electrons.
And then to solidify your knowledge, why does the wire move? You can pause and answer these questions. What happens if you flip the magnet over so the south pole is now on the left side? And what happens if the current direction is reversed? And how could you increase or decrease the amount of movement in the wire? And to investigate an interactive animation of the field lines, do a search for MagLab field around a wire, or write out all of that. I think a Google search for MagLab field around a wire may be quicker. And thank you, Mr. Godwin's 10th grade class, Team Science at Washington International School, for access to the labs using the equipment and Mr. Godwin's very useful instructions.